Okay, so let's look at a couple of examples and get some feeling for equilibria. So here is the Battle of the Sexes game that we talked about just a little bit ago. So here we have no dominant strategies. So the decision of the row player depends on what the column player is doing. So if they want to go, whether or not they choose L or P depends on whether or not they think the other player is going to choose L or P. So if the other player is choosing L, if the column player is choosing L, then the best response of the row player is L. But in contrast, if the column player is choosing P, then the best response of the row player is P as well. So the dependence here of what the best reply is depends on the other player's strategy. And if we're looking for stable points, here we can see that LL, if they're both playing L, then the 3 is the best response for the row player. So 3 choosing L gives them the maximum payoff. The 1 here is also the best response for the column player. So we have a situation where we have a stable set of strategies. LL is an equilibrium. Now obviously that favors one of the players. The row player gets a higher payoff from LL than the column player does. And the structure of this game is such that if we reverse things and instead we have the players choosing PP, that's also going to be an equilibrium. So we end up with a best response of choosing P for the column player if the row player is choosing P. We also end up with a best response of the row player choosing P if the column player is choosing P. So in this game, there are 2 pure strategy Nash equilibria, which are the combinations of LL and the combinations of PP. So it's basically a form of a coordination game where we end up with having 2 equilibria in pure strategies. There will also be one in randomization that we'll talk about a bit later. But for now, we can focus on the pure strategy equilibrium, which is one where they both coordinate on L or they both coordinate on P. Okay, so let's take a look at another example. This is one where we are looking at 2 players who have to both choose technologies. They can either choose an old technology or a new technology. They benefit from coordinating, so I'd like to match my technology use to what the other people are doing. So it might be a friend, a co-author, somebody I'm exchanging files with, something. I want a compatible system. So we can either both use the old system, both use the new system. Those are going to turn out to be the natural equilibria here. So if the other person's using old, then I get a payoff of 1 from using old and 0 from using new. If the other person's using the new technology, I get a payoff of 2 from using the new and 0 from choosing the old. So what I'd like to do, again, my best response depends on the other player. If the other player is choosing old, my best response is old. The other player is choosing new, my best response is new. What do we end up with? We end up again with 2 different equilibria, old, and new. So here's a situation where we could get stuck at the old technology. If we're both using the old technology, nobody wants to move away from it without the other player also moving away from it. And if we're both using the new technology, then that's stable as well. So there's 2 stable equilibrium points to this game. One obviously is better for both players than the other. We'll talk about that a bit more later. But notice that nobody has an incentive to move away from old. So here there's a strict benefit if you think the other person is going to stick with that technology, to stick with it too. So in order to move away from old, you'd need some sort of coordinated movement in order to overcome this in this particular game. Okay, here we can take a look at a third example. Very similar again, another form of a coordination game. Again, we have 2 equilibria. And here, whether or not, this is our collective action game that we talked about earlier, whether I want to revolt or not depends on what the other player is doing. If the other person revolts, then I choose to revolt. So if you look at the column player's payoff, the column player gets a higher payoff from revolting if the other player revolts. But if the other player chooses not to revolt, then they would prefer not to revolt. And there's some risk from revolting if the other player doesn't. So you don't want to be the only person showing up at a protest or a revolt. So in this situation, again, we have 2 equilibria, 2 Nash equilibrium pure strategies. both revolting, if that's what they expect, neither one wants to change that. But if they both expect the other person not to show up, then they strictly choose not to show up. So again, this is a game where there's two equilibria, and we can begin to see that coordination and communication and other kinds of things are going to be important in making a revolt work, because if you can't coordinate and be sure other people are going to show up, you don't want to show up yourself. So the basic essence of this game is captured here in terms of Nash Equilibrium, and we see quite clearly the importance of communication. Not revolting is a safer strategy in some sense. I get 0 for sure, and there's a risk of revolting if I'm not sure the other players are. Okay, let's take a look at one last example. This is another simple coordination game, but here this one makes the point that it's possible that there's equilibria that involve weakly dominated strategies. So in this particular case, if we look at the payoffs of this game, well, if I'm the role player and I have a choice of either going to the movies or staying home, I'd like to go to the movies if the other player goes to the movies. I'd rather stay home if the other player doesn't. So I get a payoff of 1 from going to the movies if the other player does, 0 if I stay home. If the other player stays home, so suppose that the column player stays home, what does the role player want to do? Well, they're actually indifferent between the two different payoffs in that case. They get 0 from going to the movie or staying home. So actually in this case, if the other player is going to stay home, I'm indifferent between going to the movies and staying home. So again, we'll find two different equilibria. In this case, both staying home is an equilibrium, but also both going to the movies is an equilibrium. So again, we have two different equilibria. This game is an interesting one in the sense that this going to the movies is actually a dominant strategy. So it's a weakly dominant strategy. It weakly dominates the other strategy in giving at least as high a payoff and sometimes a higher payoff than staying home. So in some sense, we might say that the logical solution of this game is both going to the movies, but that's not what's solely picked out by Nash Equilibrium. Both of these combinations are Nash Equilibria, both going to the movies, both going home, and we'll have to invoke some additional reasoning in order to make a prediction that we think that the people would go to the movies in this case. Okay, so let's talk a little bit about why Nash Equilibrium might be justified, at least in some circumstances. So the basic point of an equilibrium concept is that it's a self-fulfilling concept, meaning that if each person anticipates that the others will be playing according to what the equilibrium strategies are, then there's nothing better that they can do for themselves. So by definition, we required that each player was maximizing, and that means that there's nothing better they can do. Now, that doesn't mean that there's nothing better that the whole society can do. We saw that in a prisoner's dilemma. But it does mean that each individual can't do any better than what the prescribed strategies are. It also means that players don't have any regrets after the fact, so that they wouldn't want to go back and change the strategy they're playing. Now, when we talk a little bit about randomization later on, it could be that if players are randomizing, then the realization that they get is ex post something they'd want to change, but they don't regret the strategy they're taking in its basic form. Now, along with this, that also means that any point that's not in equilibrium is not stable, in the sense that somebody could do better by changing their action. So there's an improving deviation from any non-equilibrium point. And so while it might not be so obvious in some circumstances that everybody realizes what an equilibrium point is, it's also true that any non-equilibrium point should eventually unravel if players are maximizing and pushing in directions that improve their utilities. So that the non-equilibrium points might be more ephemeral than equilibrium points in some basic sense. Now, of course, when we look at games that have multiple equilibria, it's not obvious how one gets selected versus another, especially if players are not able to communicate or coordinate. It's not always obvious that players completely understand the game or have the full rationality or that everybody has the information. So more generally, we'll have to look at understanding processes that might lead to equilibrium. We'll have to understand things like how players play if they're uncertain about what the structure of the game is. So there's a whole series of issues that expand around the basic concept of Nash equilibrium. But it's a great jumping off point, and it's sort of the most basic and fundamental concept in game theory, and one that gives us an anchor from which we can begin to elaborate and understand more generally what might happen in more complicated situations.